Dear friends, I am Dr.S. Anbuselvi, Associate Professor, PG and Research Department of Chemistry, Sri Sharda College for Women, Autonomous, Salem. In this video, we are going to see certain important aspects of quantum mechanics, such as de Broglie Theory, Heisenberg Uncertainty Principle, and Photoelectric Effect. Wave-particle duality. We know that light source dual nature, that is, it begins as wave as well as particle. De Broglie suggested that like light, the subatomic particles such as proton, neutron, electron, positron also behaves as a wave as well as particle. This leads to the basic concepts of de Broglie theory. This de Broglie theory, that is de Broglie wavelength, is more significant for smaller molecule like electrons, and it is negligible for macroscopic object because their mass is large. If mass is large, we know that mass is inversely related to lambda. Mass is inversely related to lambda, that is wavelength. So, if mass increases, automatically lambda is very small. The de Broglie equation is lambda is equal to h by mu. Here, lambda is the wavelength of the particle, h is the Planck constant, m is the mass of the particle, and v is the velocity of the particle. Next, let us see the de Broglie equation derivation. This equation is derived by using two relationship. One is Einstein's mass energy relationship, that is E is equal to mc square, and Planck equation, E is equal to h mu. While comparing these two equations, we get h mu is equal to mc square. We know that this mu is equal to c by lambda. So, substitute the c by lambda value instead of this mu. So, we get h, for mu we substitute c by lambda. So, hc by lambda is equal to this mc square. While rearranging this equation, we get lambda is equal to h by mc. This is for light radiation. This is for light radiation. For electron, we know that the velocity of electron is represented by the letter U or V. Velocity of the light is represented by the letter C. So, for applying this theory to electron, we use U instead of this C. So, lambda is equal to h by mu. We know that mu is equal to P, that is the momentum of the particle. The momentum of the particle. So, lambda is equal to h by p. This is the de Broglie equation. The wave nature, we know that electron is a particle, but the wave nature of the subatomic particles such as electron is proved by the experiment called Davison-Germer experiment. In this experiment, the electron are produced from the hot filament, and this electron is allowed to strike on the nickel target. The reflected rays are recorded using the movable detector. That is the Davison-Germer, found that the impact of electron resulted in the production of diffraction pattern which were similar to those given by X-ray. We know that X-ray possesses wave character. So, similar to X-rays, the diffraction pattern for electrons are obtained. This gives the direct evidence for the wave character of electron. Under this de Broglie theory, I have given two problems. One is calculate the de Broglie wavelength of electron moving with a velocity of 1.20 into 10 power 5 meter second inverse. The de Broglie wavelength is lambda is equal to h by mu. H is the Planck constant, which is 6.626 into 10 power minus 34 joule second. M is the mass of the electron, which is 9.1 into 10 power minus 31 kilogram. U is the velocity of the electron, which is given as 1.20 into 10 power 5 meter second inverse. We know that joule is equal to kilogram meter square second minus 2. Second minus 2. So, instead of this joule, we can write joule only. For joule only, we can write kilogram meter square second minus 2, and for this second also I write here. Okay, in the denominator as 1 kg, here is 1 kg cancel, this meter and this one of the meter is cancel, this second inverse and one of the second inverse is cancel, and here is one s and this remaining s inverse get cancelled. Therefore, after calculation, the unit is 10 power minus 9 m, 6.068 into 10 power minus 9. The remaining unit is m. Similarly, the second problem, calculate the de Broglie wavelength of a body of mass 1 kg moving with a velocity of 2000 meters second inverse. Here the velocity is given 2000 meters second inverse, mass is given 1 kilogram. So after substituting all those things as in the previous sum, we get the lambda as 3.313 into 10 power minus 37 m. Another important quantum mechanical aspects is Heisenberg Uncertainty Principle. It says that it is impossible to determine both the position and momentum of the smallest moving particle simultaneously and accurately. The mathematical equation is del x into del p is equal to greater than equal to h by 4 pi. Here del x is the uncertainty in position, del p is uncertainty in momentum, and h is the Planck constant. In classical physics, we can measure both the position and momentum of an object precisely. Because classical physics means it deals with the big object. But in quantum world, Particle like electrons behave both like particles and waves. Because of this wave-like nature, if you try to measure exactly where the particle is, that is, the position of the particle, its momentum becomes uncertain. If you try to measure exactly how fast it's moving, that is momentum, then the position becomes uncertain. This Heisenberg Uncertainty Principle is applicable only for small object. This is not applicable for large object. Consider a photon incident on a particle. If the particle is of reasonable size, its position or velocity will not be altered by the impact of light photons. Hence, it will be possible to know exactly both the position and velocity of the particle. That is, if the particle is of a reasonable size. Suppose this cannot be so when the particle is extremely minute, such as electron. The path and velocity of an electron after the impact of light photon may be quite different from the original path and velocity. So, in the view of Heisenberg Uncertainty Principle, the Bohr model, in which the electrons are considered as particles revolving in definite orbit, cannot hold good. It is more correct to say that the electron belongs to definite energy level and not that it belongs to a definite orbit. So, after the Heisenberg Uncertainty Principle, the concept of orbit does not hold good. The concept of orbital came into existence. Here also there are two problems. The first one is a microscope using suitable photon is employed to locate an electron in an atom within a distance of 0.1 angstrom. That is, del x is 0.1 angstrom. What is the uncertainty involved in the measurement of its velocity? They are asking del v. Given is del x and they are asking del v. Our Heisenberg Uncertainty Principle is del x into del p is greater than or equal to h by 4 pi. We know that we have already seen del p is equal to mu. Mass is constant. So, the variable is only the velocity. Therefore, del p is also written as m, constant mass, into del u. After substituting all those things, we get the value of del u as 0.579 into 10 power 7 meter second inverse. In this case, the distance, uncertainty in the measurement of position is given in the unit 0.1 angstrom. But it is more convenient to represent this in meter. We know that 1 angstrom is equal to 10 power minus 10. 1 angstrom is equal to 10 power minus 10 meter. So, instead of angstrom, we use meter. Similarly, in the example 2, the cricket ball weighing 100 gram, that is macro object, is located within a distance of 0.1 angstrom. Again, here also we calculate the uncertainty in the measurement of velocity, but it is in the previous case it is very big, that is 0.579 into 10 power 7 meter second inverse, that is 579 into 70. Here the change in velocity, uncertainty in the measurement of velocity is 0.527 into 10 power minus 22. Think of how small the value is. It is highly negligible. It means that for big object, it is easy to measure both position and momentum precisely and accurately. Therefore, there is no uncertainty in the measurement of its position velocity while measuring simultaneously. That is why for big object the Heisenberg Uncertainty Principle does not valid. Now next let us see photoelectric effect. Photoelectric effect means when a light of certain frequency strikes the surface of the metal. This is the metal surface of the metal. What happened? Electrons are ejected from the metal. Electrons are ejected from the metal. A few metals shows this effect under the action of visible light, but many more shows this under the action of more energetic ultraviolet light. We know cesium, which is the alkali metal, and also we know it has lowest ionization energy, so that it can eject electron more easily, so it is widely used in photoelectric cells. After making careful studies of photoelectric effect under different conditions, the following observations are made. For each metal, a certain minimum frequency of incident light is needed to eject electron. That minimum frequency is called threshold frequency. Below this threshold frequency, there is no ejection of electrons. And this threshold frequency is represented by the letter mu0, which is different for different metals. Threshold frequency is different for different metals. Next one is first we see the threshold frequency. What is threshold frequency? If we continuously pass the radiation through a metal surface, then there was a minimum frequency below which there is no ejection of electron. The minimum frequency is called threshold frequency. Next, kinetic energy. The kinetic energy of ejected electron is independent of the intensity of the incident light, but varies linearly with its frequency. Kinetic energy is directly proportional to frequency, and kinetic energy does not depend upon intensity. The number of ejected electron from the metal surface depends upon the intensity of the incident radiation. If the intensity is more, then the number of ejected electron is more, but does not affect the kinetic energy of the ejected electron. The greater the intensity, the larger is the number of ejected electron. The number of ejected electron from the metal surface depends on the intensity of the incident radiation. And the photoelectric effect cannot be explained with the help of the classical theory. It is well explained by quantum theory. In the view of classical theory, the light of any frequency, if made sufficiently intense, it can cause the ejection of electron. But this is not happen. According to quantum theory, light consists of bundles of energy called photon. The energy of each photon being equal to h mu. Mu is the frequency of the light. When a photon of light of frequency mu0, that is threshold frequency, strikes an electron in a metal, it imparts its entire energy to the electron. This energy enables the electron to break away from the atom from the metal surface. Thus, each photon can eject one electron. If the frequency of light is less than mu0, then there is no ejection of electron. If the frequency of the incident radiation is greater than the threshold frequency, then the excess energy is used as the kinetic energy of the ejected electron. The kinetic energy is given by half mu square. Of mu square. That is, according to Einstein, this is the energy of incident radiation, which is equal to work function, that is h mu 0, that is threshold frequency. Threshold frequency plus kinetic energy. Kinetic energy. This is of mv square. Threshold frequency, that is the minimum energy required for the ejection of electron. Pi is equal to h mu 0. While substituting the pi value in the equation 1. By that is h mu 0 in equation 1, we get the kinetic energy as h mu minus h mu 0. Thank you.